Assalamualaikum, my name is Muhammad Mukri bin Razali and my metric number is B11231048. So here's my group members: Muhammad Hafiz Azri bin Muhammad Nudin, Akif Faris bin Fauzi, Muhammad Faris bin Yahya, Leonard Anthony and Alaki Matthew, and our beloved lecturer, Prof. Mayati S. Dr. Zahir bin Hassan. So I'm going to explain about our last lab, which is parallel counterflow. So for introduction, heat exchangers are fundamental components in various engineering systems, playing a crucial role in transferring thermal energy between fluids without mixing them. Their applications span across power plants, chemical processing, HVAC systems, and refrigeration, where efficient heat transfer enhances energy conservation and process performance. This laboratory experiment focuses on analyzing the heat transfer characteristics of both parallel flow and counterflow heat exchangers. By examining how different flow rates affect the temperature profiles and heat transfer efficiency, the experiment aims to demonstrate the principles of thermal energy exchange, evaluate the effectiveness of different flow configurations, and determine key parameters such as the overall heat transfer coefficient. Understanding these concepts is vital for optimizing heat exchanger design and operation in real-world thermodynamic systems. Through systematic data collection and analysis, the experiment provides insights into how flow arrangement influences heat transfer performance, ultimately guiding the development of more efficient thermal systems. Thank you.
Now I will explain about work process. Number 1, initial inspection and setup. Check all equipment and valve, fill hot and cold water tank to the required level, connect drain hose and verify connection. 2, heating and temperature stabilizer. Turn on power and hot water heater, set heater temperature to 60 and wait until hot water stabilize. 3, heat exchanger connection. Mount heat exchanger on the base unit, connect hot and cold water line for parallel flow, then switch to counter configuration as needed. 4, flow rate adjustment and data collection. Set desired flow rate for hot and cold water circuit. Turn on pump and allows the system to reach steady state. Record inlet and outlet temperature hot and cold. Repeat for different flow rate and flow configuration. 5, shutdown procedure. Turn off pump and heater. Close valve and drain excess water is necessary. Disconnect pipe connection. Turn off main power. That's all. Thank you.
Welcome to Lab 5, Parallel and Counterflow, Heat Exchanger. In this experiment, we investigate how heat is transferred in the heat exchanger system by comparing two flow configurations, parallel flow and counterflow. The aim is to observe the temperature behavior of hot and cold water under different flow directions, and to understand how flow configuration affects heat transfer efficiency. The experiment is conducted using a concentric tube heat exchanger connected to a base unit. The procedure begins by turning on the main switch and opening the water valves for both the hot and cold water supplies. The valves are kept open to allow continuous water flow. The pumps are activated to circulate water through the system. Next, the base unit is switched on and the temperature controller is set to 60 degrees Celsius. The hot water is allowed to heat up until it reaches the set temperature. Once this temperature is achieved, the system is ready for experimentation. In the parallel flow configuration, the hot and the cold water are arranged to flow in the same direction through the heat exchanger. The hot water flow rate is maintained at a constant 3 liters per minute. Meanwhile, the cold water flow rate is varied in stages from 3 liters per minute, 2 liters per minute, 1 liter per minute, and 0.5 liter per minute. For each setting, water is left to circulate for approximately 5 minutes to allow system to stabilize. After stabilization, temperature readings are taken from various points on the heat exchanger. Once the parallel flow test is completed, the system is reconfigured for the counterflow setup. This is done by swapping the TC1 and TC2 pipe connections, so that the cold water now flows in the opposite direction to the hot water. The experiment is then repeated using the same cold water flow rate variations. For each case, the water is allowed to flow for 5 minutes before recording the corresponding temperature values. This concludes the procedure for Lab 5, Parallel and Counterflow, Heat Exchanger. Thank you for watching.
Assalamualaikum. My name is Muhammad Farid bin Yahya. I will present the result for this table is counter flow. From the experiment, we can record the data TH1, TH2, TH3, TC1, TC2, and TC3 in experiment. For other data, we need to make calculation using formula given in the lab sheet. The table show the result of a heat exchanger test with different cool water flow. It include flow data, temperature, and how much heat was transferred. For this table is parallel flow. At the same table there, the experiment we can record data TH1, TH2, TH3, TC1, TC2, and TC3. For other data, we need to make calculation using formula that's given in the that sheet. For the experiment, as the cool flow rate get lower, the cool water heats up more, but the system become less efficient at transferring heat. The energy balance is good in all tests, and the data show that there is a trade-off between how much the cool water heats up and how efficiently heat exchanger works. Okay, this is our graph for the experiment. The y-axis is temperature and the x-axis is the position. The two graphs look at the same but different the data from the experiment. The graph show how hot and cool fluid charge change temperature in parallel and counter flow heat exchanger. In parallel flow, both move in the same direction, so the temperature difference drop quickly, making heat transfer less efficient. In the counter flow, they move in opposite direction, keeping a bigger temperature difference along the way, which lead to better heat transfer. This is why counterflow systems are usually more effective.
Assalamualaikum, it's me again, Muhammad Mukri bin Azali. So I'm going to continue to talk about discussion. So the discussion for this lab, as detailed in the provided documents, highlights the comparison between parallel and counterflow heat exchangers based on their temperature profiles, heat transfer efficiencies, and overall performance. So the key points include the first one, temperature profiles. The temperature distribution along the heat exchanger length for both flow arrangements was plotted using inlet and outlet temperatures, which is TH1, TH2, TC1, and TC2. It was observed that the counterflow configuration produces a more uniform and steeper temperature gradient compared to parallel flow, leading to better heat transfer efficiency. So for the second one, effect of cold water flow rate. Increasing the cold water flow rate generally resulted in higher heat transfer rates in both configurations. However, the effect was more pronounced in the counterflow setup, which maintained a higher temperature difference across the length of the exchanger, thus improving performance. So, the third one is heat exchanger efficiency. The calculated LMTD or log mean temperature difference and the overall heat transfer coefficient, which is U, illustrated that counterflow heat exchangers typically exhibit higher heat transfer coefficients than parallel flow systems. The the temperature difference between the hot and cold fluids in counterflow is maintained more uniformly, leading to better heat exchange efficiency. So the fourth one is impact of heater temperature. As the heater temperature increased, the heat transfer coefficient U also increased, indicating enhanced heat transfer performance. This is because higher temperatures create larger temperature gradients, which drive more efficient heat transfer. So for the last one is overall comparison. The study confirmed that counterflow arrangements outperform parallel flow in terms of heat transfer rate and efficiency, owing to their ability to sustain a larger temperature gradient throughout the exchanger length. So in summary, the discussion emphasizes that the counterflow heat exchanger operates more effectively than the parallel flow, especially at higher flow rates and heated temperatures, making it more suitable for applications requiring maximal heat transfer efficiency. So that's all from me. Thank you.
By the assessment rubric and instructions emphasize the following aspects. First, proper understanding the application of procedures. Students are expected to carefully read, comprehend, and accurately follow the experimental procedures related to the operation and analysis of parallel and counterflow heat exchangers. Second, systematic work process, demonstrating the ability to construct the experiment setup correctly, perform measurements accurately, and collect relevant data consistently and systematically. Third, data analysis and interpretation, ability to process the experimental data effectively, create relevant graphs and charts, and interpret results to draw a meaningful conclusions regarding heat transfer performance. Next, quality of submission, submitting clear, organized, and timely report in English with adherence to guidelines, demonstrating professionalism and discipline in academic work. Lastly, honesty and academic integrity, ensuring that all work is originally, appropriately referenced if required, and that the student demonstrates responsibility in completing the experiment and report submission. Overall, the discipline involves demonstrating responsibility, accuracy, integrity, and professionalism throughout the preparation, execution, and reporting of the laboratory activities. That's all from us. Thank you. Assalamualaikum.
My name is Akifaris bin Fauzi and my matrix number is B1123101009. So I'm going to explain the conclusion for leg 5. Counterflow heat exchangers outperform parallel flow in heat transfer efficiency. The counterflow configuration generally provides higher heat transfer rates due to the temperature difference being maintained over the length of the exchanger. Second, increasing the cold water flow rates improve heat transfer performance. At higher flow rates, the temperature difference between inlet and outlet increases, leading to enhanced heat transfer, especially in counterflow arrangement. Third, heater temperature significantly affects the heat exchanger's performance. As heater temperature increases, the overall heat transfer coefficient also increases, indicating improved heat transfer efficiency through it may plateau at higher temperature. Next, the effectiveness of the heat exchangers depends on flow arrangement and flow rates. Counterflow setups exhibit higher effectiveness and heat transfer coefficients compared to parallel flow for the same flow rates, confirming the theoretical advantages of counterflow design. Lastly, the experimental results align with theoretical predictions. Calculations based on LMTD and NTU methods show consistency with the observed temperature profiles, validating the use of these models in designing heat exchangers. This conclusion highlights the importance of flowing configuration and flow rates optimization to